These are the notes on circular motion, another kind of motion that goes round and round. With circular motion, a lot of the things we've learned about linear motion and two-dimensional motion will apply. Things about velocity and acceleration, but sometimes the equations get a little bit modified because of that little old factor of pi. You may recall we talked about acceleration before. And of course, gravitational acceleration was just a specific example of it. And then of course, Keller, did he exist? Who knows? But if he did, he was a fast guy. Okay? Faster than Remus, I guess, unfortunately. But you might not have thought about, when we talked about velocity as being a vector, that the rate at which an object's velocity changes is called the acceleration of the object. So doesn't a vector have magnitude and something else? Something else. Magnitude and direction. So if you're changing velocity, well, that could be changing the magnitude. That's what we've been doing so far. But couldn't you also change the direction? Yes. So acceleration can simply be changing the direction something is moving without changing the magnitude of that velocity. Get it? So velocities have a magnitude and direction. Changing either one can be acceleration. And when the velocity of an object changes at a constant rate, it has a constant acceleration. So you can either change the magnitude of the velocity at a constant rate, in other words, as we've been talking about, going faster and faster and faster, or going slower and slower and slower. Those are both accelerations, but so is changing the direction an object is moving at a constant rate. That is what we're talking about now. Circular motion. It goes around and around. It goes around and around the center of the circle. So what makes it go around and around? Well, it depends on a number of factors. It depends on the direction the object is moving to begin with. It depends on the forces that are applied. Remember, F equals ma, right? So is this object accelerating? Well, it looks like it's going at a steady speed, so maybe that's not accelerating. But remember, once again, velocity isn't just magnitude like speed is, it's also direction. And the direction that object is moving is definitely changing. In fact, it's going around and around, so it's going in every direction along the surface of that plane at some point. So what is making it do that? Well, it's tethered to the center in this case. This doesn't require any field forces. We're talking about a string, a tensional force. So which direction is that tensional force going? Here's the interesting part. Circular motion always requires a force toward the center of the circle. There's always got to be a force toward the center. So even though this object is not making any headway, right? It's not getting any closer to the center than it started as. In fact, that's the definition of a circle. It's keeping the same distance from its center at all points, definition of a circle. But what is happening is that it's changing direction toward the center, which keeps it going round and around. This is what a circular path is. And we can talk about the period that this takes to go around. Let's see, 1 Mississippi, 2 Miss. So it's a little bit less than 2 seconds, like maybe 1.3 seconds. We could time it more exactly. But the period is how long it takes for this object to go from where it started to the same place again, to return to the same place it started. So we call that capital T the time period, or just the period. Okay, we use the letter T because it's a measurement of time, but it's capital T. That is the period it takes for an object to move around its little circle, or big circle, could be a big circle. So here is the formula for circular velocity. Sometimes we just call this V, But just to make it clear, I'm putting a little sub c there. In this case, that just stands for circular. We're going to see another use for that little c in a minute. And how can you tell how fast that object is moving? Well, pi is pretty important here, because pi is what relates the diameter of a circle to its circumference going all the way around it. But then we're talking about the radius here, so in fact you have to double the radius to get the diameter. So we're talking about 2 pi r. 2 pi r is the circumference of a circle. It's how far it is to go around the circle. And the great thing about that is that it's usually easy to measure r. It's from the center to any point on the circle. And then we already said what capital T is. That's the period it takes to go around. So in other words, 2 pi r is the circumference going all the way around the circle, and t is the time it takes, so obviously that would be the velocity. It's the distance traveled divided by the time. So sometimes objects move because of field forces like gravity in the case of the moon around the Earth, or even the Earth around the sun, or electrostatic forces like in the case of the electron around the proton in a hydrogen atom. Now, unfortunately, in the latter example, it isn't quite so neat and tidy. It's much, much, much messier than that. Anyway, so we use this formula for circular velocity in either event, whether it is tethered to the center like we saw before, with like a string connecting it physically, or if it's due to a field force, okay, like the force of gravity, that is keeping something in orbit, like the moon around the Earth. In either event, it's the same equation for circular velocity. So you might wonder, well, how can you calculate the acceleration if the speed isn't changing, if it's moving at a constant speed? Remember, that's not a constant velocity because the velocity depends on the direction, and the direction is changing. As you go around the circle, the direction of the velocity goes through a 360-degree rotation. So there is a nifty equation for calculating what they call centripetal acceleration, or AC. Centripetal acceleration is the kind of acceleration a body experiences when it's going in a circle. And the way we calculate it is by getting its velocity, squaring that, and then dividing by the radius of the circle it's moving in. So it's pretty easy to do this if you know its speed at any given moment, and assuming that it's going the same velocity around the entire circle only by changing direction. That's the only way the velocity is changing, right? So v squared over r is the formula for centripetal acceleration. So which way is it accelerating? This is the interesting part. The direction that it is accelerating is always toward the center of the circle. So you might not see it this way because it's never actually going toward the center, but it's always turning toward the center, always kind of missing the center. So if you want to calculate centripetal acceleration, this is the way we do it, and you'll see that the units work out just like any acceleration, and it still works in many of our equations, like we need this AC and F equals ma, and it works out great. So here it is again. It's a beauty. It's a really nice, neat equation for calculating the centripetal acceleration. Now, because I didn't show you how it is derived, it might be a little harder to understand why this is the acceleration, but if you can just accept the fact that it is the acceleration, well then it's easy to calculate. Velocity squared divided by radius. Boom. So here's an example of a centripetal acceleration problem. What is the centripetal acceleration of a ball on a string 2 meters long moving at 5 meters per second? So imagine that you're whipping this ball around in a 2 meter radius circle, and you're going really fast, and it's moving at 5 meters per second. So, okay, so centripetal acceleration is equal to v squared over r. So which one of those numbers is my v? Obviously, 5 meters per second. But we have to square that, and then 2 meters is the radius. Okay, so just be careful because it says the string is 2 meters long. That would be the radius. What would the diameter of that circle be? 4 meters, right? So that's a pretty big circle. You're whipping this ball around. Okay, so what's 5 squared? Well, that would be 25. Meters squared is meters squared. Per second squared is per second squared. So 25 meters squared per second squared over 2 meters. What is 25 divided by 2? Well, 12.5, 12.5. One of the meters will cancel, and we will wind up with units of acceleration, which is what we want, 12.5 meters per second squared. So that is the centripetal acceleration of a ball on a string, 2 meters long, moving at 5 meters per second. That means it is accelerating 12.5 meters per second toward the center of the circle. Centripetal acceleration is always toward the center. Another way to solve for centripetal acceleration is to substitute. Because didn't we just have that equation for velocity for v, when we're talking about circular velocity, that it was 2 pi r over t? So what if we were to substitute that instead of the v? What would happen there? Remember, we have to square whatever v is, we gotta square it. So there we go. 2 pi r over t, the whole thing squared. Okay, well that'll be 4 pi squared r squared over t squared. Huh, interesting. And then we might be able to cancel some things, like, well, we've got an r on the bottom too. We'll be able to cancel one of those r's. So what we'll wind up with is another equation for centripetal acceleration. Can you figure it out? It will be centripetal acceleration is equal to 4 pi squared, now that's 9.86960440109, r divided by t squared. So notice it was everything the top would have been when it was squared, but then one of the r's cancels. So that's another way to calculate centripetal acceleration if you know the period and if you know the radius. Of course, pi is a constant. We don't often have pi squared. That's interesting, but sometimes it gets squared. And then 4 is just a number. So all we really need to know there is how long does it take to go around? And what is that radius from the center out to the circle? That's it. So that's a useful equation as well. So why do we need another equation for centripetal acceleration? Well, because these things are easy to measure. The time period is relatively easy to measure. Just watch one spot until it comes back. Boom. And then you just have that in your denominator, and you have to, of course, square it. And then radius is easy to measure. You can just see it visually from the center out to the circle, to any point on the circle. So the reason we have another equation is just because this one can often be more practical. It's much messier, like overall the equation isn't as beautiful mathematically, but it's a lot more practical in an everyday setting. So because centripetal acceleration is always toward the center, okay, there must be a net force toward the center whenever something is moving in a circle. This force can be provided by a number of things. For example, it could be provided in this image by the tension in the cord that is holding the massive ball before she launches it. By the way, when she does release the cord, when she releases the string, it will continue to travel in the direction it was traveling at that moment, which is tangential to the circle. It'll follow the tangent, whichever direction it was moving at the moment it was released. Okay? Or it can be provided by a field force, like gravity or electromagnetism, or the strong force or the weak force. But something must be providing a net force toward the center of the circle. Well, you already know Newton's second law, F equals ma. The only difference here is we're talking about centripetal acceleration instead of just any old acceleration. So when an object moves in a circle, the net force toward the center is called the centripetal force. So F net, which will be toward the center, is equal to the mass of the object times the centripetal acceleration. This is no surprise. It's Newton's second law again. The only difference is this applies to circular motion, and that's why it has that little c there, because it's centripetal force, which of course is always toward the center. So Newton's second law applies for circular motion, just like it does for linear motion, just like it does for one-dimensional, two-dimensional motion, even three-dimensional motion. Newton's second law is just great. And it's the same one we've been using. Just realize it works for this situation as well. So now things are getting a little trickier because we've got more equations that we might need. So now we've got to be able to decide which equation do I need for this particular problem. So of course this is now a harder problem. What is the velocity of a 2.0 kilogram ball on a 3.0 meter string with a centripetal force of 9.0 newtons? So we've got an equation on the left, equation in the middle, and an equation on the right. Which of them do we need? Well, it's asking for a velocity. Only one of those has velocity. That's the one on the left. The only problem is we would need both of the other numbers there to solve for velocity. We would need the radius, I think we have that, but we'd also need the centripetal acceleration, the AC. So we need to get the AC first before we use that. So we have to use a different equation. The one in the middle, no, the one on the right. So we have to start with the equation on the right. F net equals mass times centripetal acceleration. So which of those numbers do we already have in the question? Do we have the force? Oh yeah, centripetal force of 9.0 newtons. And by the way, that is the net force. Centripetal force is the net force. So let's swap that out in place of the F net, 9.0 newtons. And then what else do we have? Do we have the M? Well, there is a 3.0 M string, but remember, that's meters. Meters is a length, not a mass. So which one is actually the mass? The mass is actually the 2.0 kilograms. So let's put that instead of the mass, okay? And then we're going to solve for centripetal acceleration for AC. Well, if you ever need to solve for a variable, you have to isolate it, get it on its own, which is a nice thing to do, remember, getting it all by itself. So we've got to break away whatever is attached to it. If something is multiplied on, what do? We divide it off. We have to divide it on both sides because it is an equation. We got to be fair and keep it equal, keep it an equation. So whatever we do to one side, we of course do to the other side. And of course, if you divide 2.0 kilograms by 2.0 kilograms, that is a wash. That cancels out. So now we've got 9.0 newtons divided by 2.0 kilograms. Well, 9 divided by 2 is going to be 4.5. And the units are going to come out the units of acceleration. Why? Because a newton is a kilogram meter per second squared. So when we divide that by kilograms, the kilograms disappear, and we wind up with meters per second squared. So now that we've solved for AC, the centripetal acceleration, we can use another equation to solve for velocity. So let's use AC equals v squared divided by r, because now we have two of those three variables. Notice that we already just solved for AC, so why don't I substitute that? I'm going to take the 4.5 meters per second squared. I'm going to swap that in for the AC, right? Does that make sense? And then, don't we have another number? We need one of those two numbers. Which one do we have? Oh yeah, we have the R. What is the R here? 3.0 meters. So that is the length of the string. Remember, the string is swinging around. That's the radius of your circle. It would be a 6-meter circle, but the radius is 3.0 meters. So now, all we have to do is solve for v squared. Well, that's our unknown variable. So if we want to solve for an unknown variable, we've got to isolate it. but it's being divided by something. So what do you do when your unknown variable is being divided by something? You do the exact opposite function. You multiply by that exact same thing. But it's not fair to multiply one side. We have to do it by both sides, 3.0 meters, okay? And of course, on the right side, 3.0 meters divided by 3.0 meters, that's a wash. It cancels out. The number cancels, the unit cancels. It's a goner. So now we can multiply the left side, 3.0 meters times 4.5 meters per second squared. Well, then we're going to have units of meters squared per second squared. And 4.5 times 3 is 13.5. 13.5 meters squared per second squared. Well, that's good because we've got velocity squared. And you obviously are going to need to take a square root to get velocity. So notice what I just did is I square rooted both sides. You can do that. That's fair. So I square rooted v squared and I got v. And I square rooted, I don't know if that, I'm not using the proper term here. I'm taking the square root of 13.5 meters squared per second squared. And then of course, when you take the square root of meters squared per second squared, we're just going to have meters per second, which is exactly what we want. So the velocity is going to be equal to, what's the square root of 13.5? Not dividing by 2, taking the square root of it, 3.67, and that is my answer. So what is the velocity? 3.67 meters per second. That's a velocity, isn't it? Yes. So that was a tricky one. That involved using two equations, square rooting, all kinds of things. A little bit of a harder problem there, wasn't it? Okay. Here goes another tricky one. Now, what is the centripetal force acting on a 5.0 kilogram ball on a cord that completes one orbit with a 4.0 meter diameter every 2.0 seconds? Okay. So you might imagine, because we're looking for the centripetal force, that we might want to start with this equation. But the only problem is to use that equation, we need centripetal acceleration, which we don't have. We do have the mass, but we don't have the centripetal acceleration. So there's no way to solve for the net force until we get the centripetal acceleration. So we got to use one of the other two. Well, you could probably guess which one, right? Right? If we have every 2.0 seconds, that's the period. That's the time period. That's capital T. So now, yes, we do have to use this one. Of course, we're going to use it. So we've got centripetal acceleration is equal to 4 pi squared r, isn't that interesting, over t squared. Now, t squared in this case is the period squared, not just the time. It's the time it takes to go all the way around once. It's the time interval, the time period. Okay, well, I happen to know pi squared is 9.86960440109. Don't ask me why I know. I just think that's a fun number. It doesn't come up a lot. You don't get to use that very much. And then 4 is just the number 4. Oh, and then we've got to have the r. Do we have the r there? What is the radius of our circle? Oh, it's the length of the cord. What's the length of the cord? 4.0 meters. So we're going to substitute that for r. And let's just put in pi. Before we square it, let's put in pi. We can just get by with 3.14. It's a never-ending, irrational number, but we can usually get by with just those digits. So let's substitute that. 4 times pi squared times 4.0 meters. Notice that pi does not have any units. Pi is a ratio. It doesn't have any units, just like the number 4 doesn't have any units here. Okay, and what's t squared? Well, we need to know what t is. T is 2.0 seconds, so that's what t is, and then that is squared, 2.0 seconds squared. Well, that's easy. Let's do the denominator first. That's a lot easier, right? So 2 squared is 2 times 2. Okay. Seconds squared is seconds times seconds. So we get 4.0 seconds squared in our denominator. And then it's interesting because in the numerator we do have pi squared, but we also have 4, and then we have another 4. So it's kind of 4 squared, which is 16, times pi squared. Let's just multiply that all at once. Okay, like I said, pi squared is 9.86, and then times 16 will give us, oh, what's our unit going to be? Well, we only have one unit up there, and that's going to remain. It's just meters. So we wind up with 157.91 meters. Is that what you got? If you multiplied, hopefully that's what you got. And then, of course, when we divide these, it'll be meters divided by second squared. It'll be meters per second squared. And we're dividing that number by 4. Okay, well, that number is pretty close to 160. And obviously, 160 divided by 4 would be 40, wouldn't it? So we'd expect to get a number that's close to 40. Let's see what we get. Oh, very close to 40. 39.48 meters per second squared, which of course are the units of acceleration. That's what you'd expect to get. So now that we've got the centripetal acceleration, why don't we go ahead and use that yellow equation now, the one on the right, to solve for the centripetal force, which is the net force. Okay, so we're going to need the mass, and we're going to need the centripetal acceleration multiplied together. Well, what is the mass? Isn't that given in the question? A 5.0 kilogram ball. Let's substitute that. 5.0 kilograms. And what's the centripetal acceleration? Isn't that what we just solved for just now? It's the number above. So let's put that in. And if we just multiply those two numbers together, boom, we will solve for our net force, which is our centripetal force. So let's see. 39.48 times 5. Okay. Oh, isn't it funny? We just got that by dividing by 4. Now we're multiplying by 5. Well, let's see what we get here. What are our units going to be, by the way? Well, kilogram, meters per second squared. Oh, yeah, there's another way to write that, isn't there? Newtons. Of course, we're solving for a force. And we get 197.4 newtons. That's our answer. The centripetal force acting on a 5.0 kilogram ball on a cord that completes one orbit with a 4.0 meter diameter every 2.0 seconds, whoa boy, is 197.4 newtons. And yes, that is the net force, because in a circular motion, the centripetal force is the net force. Boom. So now I want to throw in something here that we could have included back in our cosmology unit about a little gravity well. You may have seen these at at a museum. You may have seen where they want you to put your coin in, and then of course you lose your coin, they get more money. That's part of it. But it also demonstrates something called a gravity well. So it's sort of representative of a gravitational field, or the warping of space. Okay. The only problem is that we have friction involved here. So instead of going on and on forever, okay, the friction slows it down and it moves toward the center. So if you release your coin or a small ball, it goes around and around, and of course that obeys the laws of circular motion. Unfortunately, there is also the force of friction, which slows it down, and then eventually it drops into the center. So this is sort of similar to what planets do around the sun, except for minus the friction. There is virtually no friction as the Earth orbits the sun, because outer space is essentially an empty void, an empty vacuum. Okay? So we did not discuss this earlier when we were talking about gravitational force, because we hadn't talked much about circular motion, so I suppose I could have thrown it in, but I just wanted to at least mention it at this point. So whenever we get into centripetal force, a lot of students think I'm saying it wrong. They'll raise their hand and say, wait, don't you mean centrifugal force? Because I've heard of that one. But here's the thing. Centrifugal force, by many physicists, is not considered a true force. It is what we call a perceived force. So some people would say that centrifugal force does not exist. But yet we feel it all the time. So why is that? Well, you have to consider Newton's laws. You know Newton's first law, that an object in motion continues in motion, right? Unless acted on by an outside force. You also know Newton's second law, F equals ma, and Newton's third law is that for every action there's an equal and opposite reaction. So sometimes it gets harder to differentiate the action from the reaction. So if you're driving along in a car in a straight line, you are inside the car moving at the same velocity as the car, right? But then if you turn the wheel of the car and start accelerating the car to the left, remember that is an acceleration, let's say centripetal force acting because of the friction with the wheels and the fact that you're turning the steering wheel causes the car to move to the left. But you inside the car, well, you continue to move in the previous direction, straight ahead. So it almost seems like you're pushing against the side of the car. But what it really is the car is pushing against you, okay? You start with the friction with the road, and that causes the car to turn. And then the sides of the car are pushing on you, that causes you to turn. But from our perspective, it feels like we are pushing against the side of the car rather than the side of the car pushing against us. So it seems like we are fleeing the center of the circle. That's what centrifugal means. It means fleeing the center, going away from the middle. Okay? And that's why they call it a perceived force. Because if you look from the outside, what is really going on is the car is turning sort of into you and you are inside the car. But the way it feels to the passenger is that you are being pushed against the side of the car by some unknown force. So they call it centrifugal force. So that is why many physicists do not like to talk about centrifugal force a lot, or if they do, they like to discount it as a non-existent force. I, on the other hand, consider it a force because in a relative sense, it is a force. Anything that causes a push or pull on an object is a force. And it's just based on your relative motion, your relative perspective or frame of reference. Okay, so let's not get too deep into this, but just realize if you're wondering about centrifugal force, it is actually the product of centripetal force. That's the quickest way to describe it.